Okay, so the next talk will be given by Ning ChenSun, and he will talk about progenitors of type 1bn systems.
So good morning. I'm Ning ChenSun from the University of Sheffield. So first of all, I need to apologize. The proposed title of my talk is Progenitors of Type 1bn Supernovae, 2006 JC and 15G. But since then, our research has evolved a little bit. So today I'm going just to talk about the first supernova, and I give my talk a more proper title as the possible binary companion of this supernova's progenitor. And here is a brief outline of my talk. My collaborators include Justin Meng, who is sitting there, and also Paul Crowder, and maybe more in the future. So first of all, this panel shows the spectrum of 06JC, which is very typical for this kind of supernovae. This spectrum can be considered as the type 1c type 1c spectral plus many narrow helium lines. Here, type 1c spectral means there is no hydrogen or helium. So that means the exploding star is deficient in hydrogen and helium. The hydrogen and the helium envelopes have been removed in some way. Here, the narrow helium lines, they indicate the presence of circumstellar material. This circumstellar material, they reside just surrounding the exploding star, and when it interacts with the supernova's injector, it will produce these very narrow helium lines. So there can be two possible channels which lead to such two consequences. First of all, if we just consider a single star, of course, the very powerful stellar wind and eruptions can remove the envelope and produce such a circumstellar material. But if we consider this star to reside in a binary system, as it evolves, it will fill the Roche lobe, and then it will lose its envelope through Roche lobe accretion or through common envelope evolution. And this could also be responsible for the generation of this circumstellar medium. For 06GC, there is another very interesting phenomenon. In 2004, just 2 years before it became a supernova, there is the optical transient right at the position of the supernova. It persists for a few days, and it looks much like a outburst coming from a luminous blue variable. But it remains an unresolved problem where this outburst comes from. It can come from the progenitor itself, but as I have mentioned, the progenitor doesn't have hydrogen or helium, and such a star has never been observed to produce such an outburst. Alternatively, this may be a binary system. It contains a Wolf-Rayet star, which becomes the supernova, and it also contains a luminous blue variable, which is responsible for this outburst. So from this discussion, we noticed that binary systems could be very important, and its interaction could play a very important role for producing such type 1bn supernovae, and also in such a special case of 06JC, it can be very important for us to understanding this precursor outburst. So in 2010, Hubble observed this supernova 4 years after it has exploded. It used the advanced camera for surveys, and it has detected a very faint source here. The supernova itself has faded, so this source is most likely to come from the binary companion to the progenitor of this supernovae. So this can serve as evidence as the binary interaction could be very important for producing such a supernova. But unfortunately, the properties of this binary companion has not been very well constrained. This is illustrated by the HR diagram, as the fitting result shown as the red contours here, they cover a very large range in the parameter space. This is because the observations is carried out in the optical wavelengths. So the optical wavelengths photometry cannot break out the degeneracy between the effective temperature and the extinction. And in order to break such a degeneracy, we do need a UV filter. So in this work, we have used the data from the HSD program, UV sensors of the size of the core collapse supernovae. It has used the Wide Field Camera 3 on board of the Hubble Space Telescope, and in order to achieve deep photometry, it has used two filters. One is the extremely wide UV filter F300X, and the other is the extremely wide B-band filter, the 475X. So we have aligned the images, and just at the supernova position, we do detect a source in the UV filter. The signal-to-noise ratio is better than 5, so we are very confident about it. In the 475X, the photometry package also reports a detection, but in the image, we cannot see the PSF very well sampled. So trying to be conservative, we regard this value as the upper limit. We notice a very interesting thing when we compare the new data points, which are the black points here, in comparison with the previous data points acquired by ACS. So you may notice that the optical flux is smaller than the previous optical flux acquired by ACS. So if we insist fitting all the data points with a single stellar spectrum, this red line is the best we can get. So you may notice it doesn't provide a satisfactory of the fit of the data points. So we have to confess that this source has changed. The optical flux has dimmed over 7 years, from 2010 to the year before last year. So here we provide one possibility, that is the extinction has changed. The extinction has increased because of the newly formed dust. So dust will be the topic of many today's talk. And there has been much observational evidence of newly formed dust for this 06JC supernova. For instance, if you look at the SED, you may notice there is the infrared color excess, which arises from the newly formed dust. And also, Martinez et al. Has noticed an increase of extinction corresponding to AV equals 2.8 of the supernovae, which arise from the newly formed dust. So there has been a substantial amount of dust being formed in these supernovae. So if we consider such a scenario that the newly formed dust and the dust material expand when it reach the line of sight between the star and the observer, and it continue to expand, we will observe a larger and a larger amount of extinction. So if we adopt such an assumption, we can provide a very good fit to the observational data. For instance, here the red and the black lines correspond to a hot supergiant, but they have different extinctions. The extinction increased by EB minus V equals 0.2 over 7 years. And also very interestingly, despite this complication of changing extinction, our new data points can still provide very useful constraint of the properties of this binary companion. Here I show again the previous fitting result based on the optical data from ACS. And if we incorporate the F300X filter and also the new optical filter data, then the possible location of this binary companion shrinks very significantly. So this binary companion must be a very hot star with effective temperature larger than 20,000 Kelvin. And this is because, well, the extinction has changed, but this star is still detectable in the UV filter. So if this star is not hot enough, it will not be blue enough, and it will be not detectable in the UV filter. So it has to be very hot. Also, this shaded regions shows the typical regions of luminous blue variables, and our fitting result doesn't overlap with these two regions. So that means this binary companion is just a normal supergiant. It is not very likely to be a luminous blue variable, the precursor outburst that I have mentioned previously, it may just come from the progenitor itself. It is not likely to come from the binary this binary companion. Also, this dark shaded region corresponds to the model predicted locus of the binary star when the primary star explodes as a supernovae, and we notice that this faded region is very well consistent with the model predictions. So this can serve as evidence that binary interaction may have indeed play a very significant role in such a supernovae. Thank you. So finally, to summarize, we have obtained new detection in the UV and optical filters after 11 years from the explosion. And the flux in the optical bands has decreased by a factor of 2 or 3 from 2010 to 2017. Here we propose that this could possibly originate from increased extinction corresponding to EB minus V equals 0.2 magnitude. And if we adopt this assumption, this binary companion must be very hot. It is much hotter than 20,000 Kelvin. It is not likely to be an LBV. The precursor outburst should come from the progenitor itself. And also the location on the HR diagram is consistent with the BPAS models of binary interaction. So all this can reinforce the importance of binary interaction in producing this type 1bn supernovae. However, we do notice there can be other possibilities for the observations. For instance, if this is a variable star, this star has changed over 7 years. That could be possible, but our current data set is not able to confirm or exclude such a scenario. Also, this may not come from a star. It is simply a light echo from the supernova itself. But here we notice that even in this scenario, we still need to consider the extinction because the light echo color should be, the predicted light echo color is bluer than the observed ones. So the light echo itself must have been reddened by the dust. So I stop here and thank you very much.
Thank you, Ning Cheng. Do we have any questions?
Nice results. 1BN are actually one of the most observational heterogeneous class you can get in core collapse supernovae. So do you have similar data or you can obtain similar data for an identical kind of 1BN supernova like 06JC to confirm that possibly they were coming from similar binary scenario because you have something like between 10 and 15 different observational properties in 1BN, which would suggest a different kind of binary systems. But if you can pinpoint the binary system, which you're getting the same results, even for the progenitor, comparing to 2 identical 1BN, that could actually strengthen your case. Do you have anything like that, or do you think you can get anything like that?
Well, I should apologize. I didn't quite get your point. So can you just speak slowly?
You pinpoint a progenitor scenario with a kind of supernova. And if you take another supernova that shows the same light curves, very similar, or same spectra in terms of velocity and elements of 06JC, and is nearby enough, you can get similar observation, you should get most likely the similar results. So my question is, do you have another object? It was 15G like that, or was different in terms of velocity and spectral properties of 06JC?
Yes, actually 15G is another type 1bn supernovae, which is very similar to 06JC. Actually, we are doing some analysis with more such kind of supernovae. But here I can tell you that for 15G, we didn't detect any binary companion. Well, this is because even for 06JC, the detections are very close to the detection limits. So this is actually a very challenging problem. For other type 1b supernovae, well, the thing is how much observational material we have. So we need to apply for more observational data. Yeah. So does that answer your question?
Yeah.
All right.
Time for one quick question, Dan.
Are you certain that the light you're seeing is not still remnant supernova light? Because there's a lot of interaction going on, and that would be consistent with it going down with time as well.
Well, the supernova, it has been estimated the supernova's own light has faded enough. So even in 2010, the light shouldn't come from the supernova itself.
As extrapolated.
That's right.
Because I just wonder if it reaches a reverse shock stage, because there's all this CSM, if there could be a new contribution. That's all.
Well, for that, well, it's really hard to say. That really depends on the detailed geometry of circumstellar material.
I'm not sure either. That's why I asked if you consider it. But you seem to think that at that stage it would not be contributing to it. Right.
From the interpolation itself, it should be faded enough.
Okay, let's thank Ning Chen again.